Welcome to today's Explainer. We're about to set off on a pretty incredible journey through the world of energy generation. We're going to start off really small, looking at microgenerators and modular power systems, and then we're scaling all the way up to harness the massive raw forces of the ocean. It's just a fascinating look at exactly how we capture power from our environment, whether that's through, high-tech fuel cells or literally the gravitational pull of the moon. Let's get into it. So here's our roadmap for today. We'll start with distributed energy and renewables, move into the power of tides, then calculating tidal energy, followed by ocean wave kinematics, and wrap up with grid integration challenges. All right, Section 1, distributed energy and renewables. Now, fuel cells are absolutely fantastic because they give us the secure, continuous power output with zero or at least very low emissions. Plus, they're modular, right? So we can drop them right into a distribution system without worrying about geographic limits to get the best bang for our buck. But, well, they definitely aren't perfect. That high initial cost? Yeah, that's a major roadblock. And critically, they just can't respond quickly to electric load transients. If power demand suddenly spikes, a fuel cell simply can't just throttle up in an instant to meet it. It's a real bottleneck. So when we're evaluating the fuel efficiency of local generators, like microturbines, we really have to distinguish between two specific values. You've got your higher heating value, or HHV, and your lower heating value, LHV. The HHV is the gross heat of combustion, meaning it actually includes the latent heat. The LHV, on the other hand, is just the net heat of combustion. Knowing this difference is absolutely vital so our engineers aren't accidentally overestimating the true usable heat output of these small but mighty power plants. And speaking of mighty, 96,000. That is the staggering RPM achieved by these refrigerator-sized capstone microturbines. What makes this so wild is that these turbines only have one moving part. It's just a single common shaft holding the compressor, the turbine, and the generator, and it spins it up to 96,000 revolutions per minute, entirely on air bearings. To put that into perspective, your car engine probably redlines at, 6 or 7,000? So these things are screaming fast. Because of that, there's literally zero need for lubricants, no gearboxes, no coolants. It radically drops maintenance needs while still pumping out up to 60 kilowatts of power. Transitioning over to solar for a second, we run into a really unique challenge: pulling maximum power out of photovoltaic arrays. Since a PV array has nonlinear characteristics and, the Earth rotates, we have to use something called maximum power point tracking, or MPPT. There are two main setups for grid-connected PV systems: the conventional two-stage and the single-stage configuration. By using these super precise power conditioning systems, we can extract the absolute optimal amount of power and feed it directly into the AC grid. No bulky battery backups required.
Okay, moving on to Section 2, the power of tides.
Now, before we go trying to harness the entire ocean, we need to define exactly where these incredible hydro projects actually live. An estuary is essentially a part of a river or stream that's influenced by the tide in the main sea. It's the mouth of the river, right where that river current actually meets the tidal current. And this specific, highly dynamic geographic spot? It is the absolute perfect canvas for building a tidal power plant. So let's look at the actual nuts and bolts of a single basin tidal scheme. At high tide, ocean water rushes in and fills up this massive enclosed pool situated behind a huge dam structure, which we call a barrage. Then, when the tide outside the dam starts to ebb and the water level drops, that barrage is suddenly holding back a massive head of water. Once that height difference is great enough, boom, the sluice gates are opened. The water is forced right through reversible hydroelectric turbines, generating massive amounts of power as it flows back out to sea. It's a brilliantly simple yet powerful concept. Up next, Section 3, calculating tidal energy. So the work done by all that water is directly proportional to the square of the tidal range. By taking standard gravitational acceleration and factoring in the average density of seawater, which is about 1,025 kilograms per cubic meter, we derive this incredibly useful little constant, 0.225. It's honestly amazing how cleanly all that complex physics translates into raw power. This one constant lets us calculate the average theoretical power per unit pool area just by squaring the tidal range and multiplying it by 0.225.
All right, let's actually put that constant to work in a real-world scenario. Step 1. Imagine we have a tidal basin area of 20 million square meters, experiencing an 8-meter tidal range. Step 2. Using our handy formula, we multiply 0.225 by 8 squared, and then multiply that by our basin area. That spits out a massive average theoretical power of 288 million watts. Then, step 3. When we convert that power into energy over time, that seemingly simple 8-meter tide translates into a staggering 10.368 times 10 to the 8th kilowatt hours of energy. When you apply the mathematical scale of this hydropower to the real world, it's just truly breathtaking.
Moving right along to Section 4, Ocean Wave Kinematics. Now, if we look past the surface of a wave and peer down into the deep water column, the kinematics are completely different. On the surface, a wave just looks like a simple, two-dimensional, progressive sine wave, right? Just moving from crest to trough. But underneath the surface, those water particles aren't actually just moving forward. They're rotating in place in an elliptical path. Near the surface, that path is almost perfectly circular, but as you go deeper and deeper, the vertical axis shrinks, and those ellipses become flatter and flatter until you finally hit the ocean floor. I absolutely love this vivid analogy straight from our source material. If the complex math of horizontal and vertical semi-axes feels, a bit too abstract, just picture placing a cork on the water. As a wave passes by, that cork doesn't just shoot continuously forward, it bobs up, slightly forward, down, and slightly back, literally tracing that exact circular path we just talked about. A wave carries both potential and kinetic energies, and it's driven entirely by this constant localized rotation of water particles.
And just to prove the sheer raw speed and power inherent in these standard ocean waves, think about this calculation. If you have a wave that's just 2 meters high from crest to trough with a 6-second period in water 100 meters deep, that wave energy is propagating at an impressive 9.36 meters per second. That is a massive amount of moving kinetic energy, literally just waiting out there to be harvested by wave energy converters.
Finally, let's get into Section 5, Grid Integration Challenges. Okay, here's where we bring all this lofty physics crashing back down to reality. You see, the typical electrical distribution grid was originally designed for a passive one-way traffic system. Power flows steadily from the substation straight out to your house. But the minute we start including renewable distributed generators, we introduce chaotic two-way power flows. When a solar array faces short fluctuations in irradiance, say from a passing cloud, it fundamentally throws off power quality and total harmonic distortion. Furthermore, if a short-circuit fault happens, inverter interface generators quickly inject reactive power, which can actually disrupt the performance of our critical safety relays. It's a real puzzle. Now, a commonly touted benefit of distributed generation is this idea of voltage support. However, take a close look at how the dotted line on this voltage profile actually drops when the unit is turned on. If you plug a distributed generator into the feeder line, it actually reduces the observed load at the line drop compensator control. This can totally confuse the regulator into setting a voltage lower than is actually required. So instead of supporting it, it's literally dropping the voltage profile on the feeder. Crazy, right? And that really brings us to the ultimate engineering challenge of our transition to renewable energy. We clearly have the technology to harvest the sun, the wind, and the incredibly massive power of the ocean's tides and waves. But how do we engineer a smart grid future that perfectly balances all this raw, chaotic natural power with the incredibly precise, delicate demands of our electrical infrastructure? It's a colossal problem we have to solve, and it certainly leaves us with plenty to think about until next time. Thanks so much for joining this explainer, and we'll see you in the next one.